Okay, so Fahrenheit, we might look at it a little bit. You're actually never going to use it in any of your calculations in actual chemistry calculations, okay? You would have to convert from from Fahrenheit to Celsius if you were given the Fahrenheit. All right? So if you're given Fahrenheit, then you would need to convert. Otherwise, you're always going to be using Celsius or Kelvin in your calculations in chemistry, okay? But this is basically measuring the temperature, right? And when you're in Celsius and Kelvin, the measurements are on the same scale. They're just offset. So here I have 0 degrees Celsius, which is 273 Kelvin. So 0 degrees Celsius is 273 Kelvin. Okay? If I went to 0 Kelvin, that is the coldest temperature possible. Okay? That is the absolutely coldest temperature possible, which is absolute 0. Okay? So the Kelvin scale is based off of absolute 0. The Celsius scale is based off of the temperature at which water freezes, 0 degrees Celsius, and the temperature at which water boils, 100 degrees Celsius. But the increments at which they increase are the same. 0 degrees Celsius to 1 degree Celsius would be 273 Kelvin to 274 Kelvin. If one goes up 1 degree, the other one goes up 1 degree. They're simply offset. So that makes the conversion between these two very easy. If you have 25 degrees Celsius, what is that in Kelvin? Well, I simply add 273 to it, and that will be my Kelvin temperature, 298 Kelvin. So you can see 25 degrees Celsius, 298 Kelvin. Okay? I simply add the Kelvin temperature. You hardly ever go the other way. Hardly ever. Okay? It's most always what is the Kelvin temperature from the Celsius temperature. So you're always adding 273. But if you were to go backwards ever, okay, if they gave you the Kelvin temperature and they wanted you to find Celsius, which is very, very rare, hardly ever happens, okay, then you would start with 298 Kelvin, and you subtract 273 from it. That's going to give you 25 degrees Celsius. Right? So it's that simple. That's the easiest conversion you're ever going to do, from Kelvin to Celsius, okay? Because the increments are the same. They're just simply offset. So in the Kelvin temperature, you can never have negative temperatures because the lowest temperature is 0. In the Celsius scale, you can. Anything below 0 degrees Celsius will be a negative temperature. So you could go all the way to negative 273 degrees Celsius, which would be absolute 0, which is very, 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 very cold, okay, and nearly impossible to obtain. Now, if you were going to convert from from Celsius to Fahrenheit or Fahrenheit to Celsius, you would use this conversion, okay? So basically, this is the one. You could just use one of these. You don't have to have both of them, okay? But you would be given this as a reference material if you needed it, okay? So to find the temperature in Fahrenheit, it equals 1.8 times the temperature in Celsius plus 32 degrees, okay? And that's how you would find that temperature. So convert 75 degrees Celsius to Fahrenheit. So here is my Fahrenheit equation. So degrees Fahrenheit equals 1.8 times the degrees Celsius, which is 75 degrees Celsius plus 32. Okay? Convert 10 degrees Fahrenheit to degrees Celsius. So here I'm going to use this equation to get to degrees Celsius, which is simply a derivative of this equation, right? It's these two things, and then you divide by 1.8. You divide by, this will equal, okay, what do I want to say? You subtract 32, that's what you need to do. You subtract 32 to that side, T delta Fahrenheit minus 32. Okay, you subtract this over here, and that's going to equal 1.8 times T degrees Celsius. And then I want to get my degrees Celsius all by itself, so I move 1.8 down. So T degree Fahrenheit equals, minus 32 equals T degrees Celsius divided by 1.8. Okay, so that's how I end up with that same equation. Don't want to get that confused. All right, so that's the equation I'm going to use. This is my Fahrenheit temperature to Celsius, which equals negative 10 degrees Celsius minus 32 divided by 1.8. Okay, and that's how we get there. And they give you those answers right there. Okay. Like I said, Kelvin temperature is just simply an offset, so you just add or subtract 273. Here, to find the Kelvin temperature from the Celsius temperature, I add 273. To be more precise, 0.15, I'm not going to require you to add 0.15, but 273, 0.15 or 273 is going to give you the same basic answer, okay? So that's how you're going to do that. Okay. Energy. Energy is our ability to perform work. Okay? There's two types of energy. You have kinetic energy and you have potential energy. Kinetic energy is the energy of motion. It's the particles are in motion. They're releasing energy. Potential energy is your stored energy. Okay? Your position determines the amount of energy that you have. Right? So this is often very well depicted as a boulder sitting on top of a hill. So this boulder has a lot of stored energy in it, sitting at the top of the hill. And as it moves down the hill, it rolls down the hill, it's releasing energy. Okay? And it's gaining momentum, it's releasing energy. And when it gets to the bottom, okay, it's released that energy, and now its potential energy has changed. It doesn't have as much potential energy at the bottom of the hill as it did at the top. So it lost energy because now it's at the bottom of the hill. We can also categorize energy in different forms: light energy, heat energy, electrical energy, mechanical energy, chemical energy. Chemical energy and heat energy are essentially the same because chemical reactions, they release heat. And that's how we categorize them, as releasing heat. And so those are kind of the same. Okay? Light energy, we can see the radiation coming off of the light right now. That's has radiation associated with their wavelengths, different things. Okay? So energy isn't something that we can create. So if I get a generator and I crank it, and I say, oh, I'm producing energy. Okay? That's true, but that energy isn't created. It's not made. It's always been there. I'm just releasing it. So energy cannot be created or destroyed. I can't destroy energy. It simply gets transferred from one thing to another thing. So when molecules are flying around in this room and they collide with one another, the energy between one of the molecules gets transferred to the other molecule through that collision. Okay? So energy is transferred. It's not lost. It's not created. Or, well, it can be lost, but it can't be destroyed. It's not destroyed or created. It's just simply always been there. The amount of energy in the universe is conserved. Okay? The amount of energy in the universe is conserved. I can't create it or destroy it. So most of the energy that we have here on our planet comes from where? Where does it originate from? The sun, right? So the sun is a big power plant producing vast amount of energy, and that energy is traveling here in the form of heat and light, and the plants absorb it, And we can use that energy here on our planet, right? We can extract the energy from different sources that has been captured here, okay? So energy conversion is never really 100% efficient. You just can't have that. In fact, if we consider the amount of energy transferred from one organism to another organism in the form of food, that transfer is only about 10%, okay? Or there's a loss of that amount every time that there's that transfer. So if you're a primary consumer and you eat plants, then you're getting the energy directly from the plant who got it directly from the sun. And so that's kind of the primary source. But then if I'm a secondary consumer, so if I eat the cow that ate the plant, then there's an even less transfer of energy because I'm getting it secondhand. I'm getting that energy secondhand instead of primarily, okay, firsthand. All right, so there's always that deficiency in the energy transfer. And all chemical reactions involve either the gain or loss of energy. So for the reaction to proceed forward, you either have to gain energy or you have to release energy. Okay? And we're going to characterize them as such. Energy is expressed in the units of calories or joules. So 1 calorie equals 4.184 joules. A kilocalorie. Here they're noting that it's a food calorie. Okay, one kilocalorie equals 1 calorie equals 1,000 calories. So this big C calorie, what does that mean? That's the food calorie. So does anybody have a candy bar? No, nobody. Okay. So let's say there's 250 calories in a candy bar. Okay. So that's a big C calorie. So what does that mean? It means there's actually 250,000 calories in your candy bar that you're eating. Okay? But the food industry doesn't want you to put that on their label, right? Because then nobody would buy their candy bar. So they say it's instead 250 big C calories, which is actually 1,000 calories for every 1 calorie. But that's okay because it doesn't really change anything except our perspective. How many calories do I need every day?
2,500, depending on what.
Okay, well, depending on the individual, but about 2,000 calorie diet, let's say, okay? How many calories is that in true calories? 2 million. So you still need 2 million calories, whether you're going to get it through your 250,000 calorie candy bar or not, okay? So it doesn't really change how much we need, it just changes our perspective, and the food industry doesn't want you to see 250,000, they want you to see 250, okay? Which now you're still thinking, well, that's still a lot, 250, right? But it's less than 250,000, okay? Not really, but that's our perception. Okay, so 1 calorie amount of heat energy required to increase the temperature of a gram of water by 1 degree Celsius. So that's kind of where the calorie is based off of, how much energy is required to change 1 gram of water by 1 degree Celsius. I have to add that much energy to cause that change, okay? But joules is also a very consistent one that we're going to use, unit of energy. All right, concentrations. We will be working a lot with concentrations in here, and that'll be based on either mass concentrations or molar concentrations. Molar, we'll learn about what the mole is. Or did we learn what the mole is? No, not yet. So we're going to learn what the mole is, and and those will be concentrations based on those amounts. So based on the grams or the moles that we find here on the periodic table, okay, those numbers. And concentrations are ratios, the amount of something in a specific area. How much is in that area? That's your concentration. It's a ratio. So I could describe it as 360 grams of something in 1 liter, right? I could describe it in that way, or I could say in 275 liters. And I could reduce that into the amount that it is in grams per liter. So 365 divided by 275. And it would tell me the ratio in grams per liter instead of it being in 363 grams per every 275 liters. And that's the concentration, is that reduced ratio. The reduced ratio, and then I would know what it is in every single liter, every individual liter, instead of in the 275 liters. And that's how we perceive these concentrations. It's in their lowest ratio amounts. Okay? So we reduce them, we simplify them into those amounts when we look at them. And density is one of those. Density is a ratio of mass in a volume. And the density of something doesn't change with the amount. So it's an intensive property, right? It's an intensive property that doesn't change with the amount because it's a ratio. It's a concentration. So this is the density equation. Density equals mass over volume. Okay? I think this pen needs to be darker. Okay, so density equals mass over volume. And I want to solve for the density. Then I need to know the grams, which is the mass, and I need to know the milliliters, which is the volume. Now, densities for gases would be expressed in grams per liters, because gases are so less dense than volumes of liquids that you don't express it in milliliters, because it would be a ginormous number if we did that. It would be a very large number. So we don't want to do that. We want to express it in per liter so that it makes that number kind of smaller, more conceivable to us. Okay? So that's for gases. But for liquid volumes or solid volumes, this is how we would describe their density, in grams per milliliters. Okay? Grams per centimeter cubed is the same as grams per milliliter. Centimeters cubed is the same as a milliliter. 1 centimeter cubed equals 1 milliliter. Okay? They're equivalent. Here, this is the same thing. Grams per centimeter cubed, cc's. Okay? That's all that means. Okay, so here we see a few things that have been identified, basically, or separated by their densities. So this is liquid mercury. It's a metal, but it's a liquid at room temperature, this metal. It's very dense. It's a very dense metal. And you can see it's much heavier than even the solid brass nut. So the liquid mercury is heavier, so the nut will not sink in the liquid mercury. It will stay on top of it. If I was less dense, than the ocean, then I wouldn't sink in the ocean. I would just sit right on top of it and float along, or I could just walk across it. But I'm not. I'm more dense than the ocean, so I will sink if I try to step in the ocean. But this brass nut will not sink in the liquid mercury. But it will sink in the water because it's more dense than the water. The cork is less dense than the water, so it stays on top. Okay? Which is why air floats, because it's less dense than the stuff around it. So I sink in the air because I'm heavier than the air. But if something is less dense than the air, then it would float in the air. So, for example, you take some air molecules, you trap them in a container, and you heat them up, and all of a sudden those particles get farther and farther apart as they heat up, and they will become less dense than the air around them, and then that thing would float like a hot air balloon, right? You have that little burner under there, you heat up the air in there, and the air expands, It becomes less and less dense, and then it lifts. It lifts that balloon up because it has become less dense than the air around it. Okay, so here's some common densities. Air has a, so if you express air in grams per milliliter densities, it's 0.00129. It's not quite how we want to look at densities in these small amounts. So we want to bring them more to these numbers so that we can see it. So a lot of times, like I said, gases are expressed rather, instead of in milliliters, in liters, grams per liters. So benzene, 0.879 grams per milliliter. Blood, 1.06. That's because blood is mostly water, and water has a density of about 1 gram per milliliter. Okay? Bone has a density of 1.7 to 2.0 grams per milliliter. Carbon dioxide is a gas, so it's a low density. Okay? Here's ethanol is a liquid. It's a volatile liquid. Gasoline, gold. Gold is pretty dense. 19.3 grams for every milliliter of it. So for just a little bit, it's pretty heavy. If you have just a little bit of it, it has a pretty good mass to it. Just like that mercury. Where's that mercury? There it is, 13.6. So gold is more dense than the mercury. So if we had that image earlier, if we put gold in here, the gold would sink in the liquid mercury because it would be heavier than it. Okay. So how do we calculate density? Well, so here's an example. We have a 2.00 centimeter cube. That's a volume measurement. Centimeters cube sample of aluminum. And it's found to weigh 5.40 grams. Calculate the density in grams per centimeters cubed and grams per milliliter. Well, that should be easy because once we find the grams per centimeter, that'll be the grams per milliliter. Okay? So density equals the mass over the volume. Here's my mass, 5.40 grams. My volume, 2 centimeters cubed. So I'm going to take my mass and I'm going to put it on top and divide it by my volume on the bottom. And then I find it to be 2.70 grams for every centimeter cubed. This is kind of like that example I gave you earlier where I was telling you we always express it in its lowest ratio. So this right here is the concentration. At every 5.40 grams, there's 2.00 centimeters cubed. But I express it in my lowest ratio, so I simplify it by dividing these by each other. And I show that now, for every 1 centimeter cubed, there are 2.70 grams in every 1 centimeter. So I've reduced it, I've simplified that ratio, and this is how I express it. So now I know how much there is in every single centimeter instead of in every 2 centimeters. Okay? And because 1 centimeter cubed equals 1 milliliter, it's the same. To go from density in centimeters cubed to density in milliliters, it's the same. Okay? So these are the same expressions. Okay, calculate the volume. Now this time, okay, so part of the problem when you guys take tests is that you sit down and you see a question. And you're like, what equation am I supposed to use? Okay? So let's kind of break that down for something like, obviously we're doing density right now, so you're going to use the density equation. But when you're in a test, there's like 50 equations, and you're like, what am I doing? Okay? So here, I can see they're saying, find the volume. They gave me a density and a mass. So because they gave me a density, that should be a clue to me that what equation am I going to use? Density equals mass over volume. I'm going to use the density equation. What do they want me to solve for? Volume. And I'll tell you, solving for volume in the density equation is one of the most difficult things that people encounter. Why? Because volume is on the bottom there. And like in that pre-math assessment, okay, this is what a lot of people do. You had a question about volume in there. And this is what a lot of people do. They say mass times volume, or they say density times volume, or they say density divided by mass equals the volume. But for some reason, they just can't get the right one, which is volume equals mass over density. This is the right equation. If you can't see that right now, then let me show you a way to make it easier. Okay? Whenever you have something on the bottom, the best thing to do is get it off the bottom. How do I get something from the bottom to the top? How do I get this volume from the bottom to the top? Okay, I multiply by volume on each side. Cancels over here. I'm left with volume on that up there. I move it up. It moves from the bottom to the top of the other side. That's what I do. I take it from the bottom and I move it to the top on the other side. Now, I hope you can easily see the equation for volume. Whenever you have stuff on the bottom and you're trying to rearrange that, it can be very confusing. So don't try. Don't try to do it when there's something on the bottom. Take it from the bottom and move it to the top. When you have everything on the top, it becomes so simple. What's my equation now? Mass equals density times volume. That's my equation. This is a very simple equation to work with, because all I have to do now is say, what do I want to isolate? I want to isolate volume. Volume equals mass, and I got to get density out of there. So I just move it under. So volume equals mass, move density down, divided by density. Okay? Now I have the equation I'm going to use. This is my equation. So mass equals density times volume is a much easier equation to rearrange than this density equals mass over volume. Okay? Because this is the hardest thing for people. I get this kind of stuff all the time. I get this all the time. Okay? So, to avoid doing it wrong, take that volume, move it to the top. This is an easy equation to work with. I can easily see that volume equals mass divided by density. Okay? So, that's what we're going to do here. So, we want to calculate the volume. Okay? And they're doing some weird stuff here. But in any case, we want to calculate the volume. The density is 1.20 grams, and the mass is 5 grams. Ignore what they're doing. That's just going to confuse you. Okay? Just set it up. If I want to find the volume, I already isolated the equation. Volume equals mass over density. Mass over density. So I take my mass, which is 5.00 grams. Oops. Okay. And I'm going to then put it over my density, which is 1.20 grams per milliliter. Now, whenever your units end up down here, divided by, then divided by, they actually go to the top. So they're going to go here to milliliters. So they go away from down there. Oops. And now you can see my grams cancel, and I'm left with units of milliliters, which is the volume that I want. Okay? This is the volume that I want. Volume equals 5 divided by 1.20 grams. Okay. You know what? I'm gonna say actually that's not such a bad way to do it. The way that they're doing that, maybe that makes sense to you. So let's go over it. Okay? So they're just saying you could take this 5 grams, and the density was given to you as 1.2 grams per milliliter. Okay, so these are your two available conversion factors for that. And if you set it up so that grams to milliliters to volume, you could use the density ratio. You could cancel out the grams and you'd be left with milliliters. Still, it's 5 divided by 1.20 either way. Okay, so I suppose if that helps you, but I just don't want to confuse you guys with all these different ways. Okay, if you solve for volume, you'll set it up correctly. Grams over density, you'll get there. You'll get the right answer. So let's try a few. Okay, so on a piece of paper, this is the density of air, 0.0013 grams per milliliter. What is the mass of a 6.0 liter sample of air? A 6 liter sample of air. What is the mass? Okay, so this is my density equation. What equation am I going to use to solve for the mass? What is the mass? Mass equals density times the volume. Okay, I have my density and I have my volume. So am I going to say 0.0013 times 6? Why not?
Because you have to convert it from liters to milliliters.
Absolutely, right? Those are not the same units. Milliliters and liters are not the same. I have to have them in the same units of volume before I can calculate this. Okay? So I need to change that 6 liters to milliliters. So how many milliliters are in 6 liters? 6,000 milliliters in 6 liters. Okay? So 6 and liters to the milliliters from the liters. There's 1 in every 1,000. 6,000 milliliters in 6 liters. So I'm going to take that density, which is 0.0013 grams per milliliter, and I'm going to multiply it by my volume, which is 6,000 milliliters. Okay, so what is my mass here? 7.8? 8 grams. Okay, so that's how I'm going to find that one. Okay, calculate the mass in grams of 10 milliliters if mercury if the density of mercury is 13.6 grams per milliliter. So, go ahead. Find the mass of 10 milliliters of mercury. Okay, so what equation am I going to use? Same one. I'm going to use the same equation, right? Mass equals density times volume. My density, 13.6 grams per milliliter. Okay, times my volume, 10.0 milliliters. Do I need to convert anything? Nope, all the units match. So 13.6 times 10, right? So 136 grams. That's how much it'll weigh. Calculate the volume in milliliters of a liquid that has a density of 1.20 grams per milliliter and a mass of 5 grams. Okay, what's my equation? Volume equals mass over density, right? So here I could start from that equation. I found it for mass, but now I can rearrange it for volume simply by moving density underneath mass. Okay? Get it from the top back to the bottom. Volume equals mass over density. So having it in this format with everything on top really helps me see what the true equation is that I need to use. Okay? So my mass is 5.0 grams, 5.00 grams, divided by my density of 1.20 grams per milliliter. My grams cancel. I'm left with milliliters. 5 divided by 1.20 is what? I'm sorry?
4.16.
Okay, so 4.17. Okay, so oops, milliliters. That's my volume. Okay, good, excellent. Specific gravity is just simply the density of one object divided by the density of another object to determine specific gravity. We're actually not going to be doing any calculations of specific gravity in here, so you won't have to really worry about it. Okay, so that is the end of chapter 1, okay, with density. And now we're going to start in chapter 4. Chapter 4 is an enormous chapter, and we're going to take it piece by piece. We're not going to go in order of the chapter either, because it's kind of in a strange order. So let me see here. Okay, so chapter 4, we're going to talk about some more conversions, okay, and also how we use these conversions in quantities for atoms that we can perceive, because we can't go measure out a single atom on the periodic or on a scale. We can't do that. But I can measure out a whole lot of atoms on a scale that have a significant mass that I can see or perceive. But if it's too little, I can't see it, I can't perceive it. It's not going to do me any good to work with it. Okay, and so we're going to look at how to do those calculations and how they relate to the chemical equation and lots of things like that. Okay, so here we're going to talk about the concept of the mole. All right. So atoms are very small. They're very tiny, right? And their masses are very small as well. So here, carbon has an atomic mass of 12. Why? How does it get that mass of 12? It's not 12 grams, it's 12 atomic mass units. Where does that number come from? Well, you can find it there, but what makes up that mass of 12?
Combination of isotopes?
Okay, okay, not necessarily a combination. So for carbon 12, it's just a single isotope. If it was carbon 12 and 13 and 14, then it would be the combination. That's how we get that number. But this carbon 12, what gives it that mass of 12? What's in the nucleus that's giving it that mass? Protons and neutrons. The protons and neutrons. It has 6 protons. That means it has 6 neutrons. Every single proton and neutron has a gram mass of 1.661 times 10 to the negative 24. So if I wanted to figure out how many grams were in a carbon-12 atom, I would say 12 atomic mass units, and I would say there's this many grams for this many atomic mass units, 1.661 times 10 to the negative 24 for every one. And I could take that 12 and multiply it by 1.661 times 10 to the negative 24 and still get a really ridiculously small number. A number that I could not measure on the scale. I can't do that for a single atom of carbon, right? So then how many carbon atoms do I really need to really work with them? So here's the atomic mass of fluorine. If I multiply that by the gram mass for every atomic mass unit, I would get this many grams for a single fluorine atom. 3.156 times 10 to the negative 23 grams. That's what that number is. There's no way I can measure that, right? On the I'm sorry, not periodic, but on a scale in the laboratory, I can't do that for one single atom. So I need a bunch of those. How many of those would I need to make it something that I could work with? Okay, well, this is how many. 6.022 times 10 to the 23rd atoms. That's the standard number of how many atoms I need to work with them, to make them so that I can work with that much. That's a humongous number, right? It's kind of the opposite of the number we just saw. Now it's a really gigantic number. Okay? That's how big that number is. I need a really big number to be able to work with really small atoms. I need a whole lot of small atoms to make it something that I can work with. Okay? So, this is Avogadro's number. Avogadro's number is a standardized number that we use to be able to work with these chemicals. So if I have that many atoms of carbon, they would weigh 12.011 grams. If I had that many atoms of sodium, it would weigh 22.98977 grams. So these are the gram mass amounts related to Avogadro's number. 32.06 grams for every 6.022 times 10 to the 23rd atoms of it. That's how many atoms I would need for them to weigh those amounts found on the periodic table. So, it's interesting that those numbers not only represent the atomic masses, but they also represent the gram masses if we have 6 times 10 to the 23rd atoms of them. Okay? So that's how this all kind of works out. So, here's my 19 atomic mass units of fluorine. If I multiply it by 1.661 times 10 to the negative 24. And then I multiply it by Avogadro's number, 6.022 times 10 to the 23rd. Guess what? I get back to 19. I started with 19, I get back to 19. This is the number that I need so that I can relate these two. The atomic mass with the gram mass amount. Okay? So, if I want to know how much I need of something, I just come here. These are the atomic masses, but they're also the gram mass amounts for every 6.022 times 10 to the 23rd atoms of it. 4 grams of helium would have 6.022 times 10 to the 23rd atoms of helium. Okay, that's a really hard number to comprehend, to conceive. That number we actually have a name for. It's called the mole. We call it a mole. Okay? Oh, well, I'm sorry. That's the abbreviation. You can see the abbreviation and the whole name. It's a big difference. M-O-L-E, M-O-L. It's hard to write M-O-L. It's harder to write M-O-L-E than M-O-L. So we go with M-O-L. The mole. Big time abbreviation there. Okay? So a dozen has 12. A gross has 144. Those are numbers that relate to the name, right? The mole is the same. 1 mole equals 6.022 times 10 to the 23rd of whatever it is. It could be pencils. It could be marshmallows. Whatever it is, if you have that many of it, you have a mole of it. In our case, we're talking about atoms or molecules. Okay? Because that's what we work with. We work with atoms and molecules in chemistry. And we have to have a whole lot of them to be able to really perceive these things. Okay. I'm going to try to find this video. Let's see where.
Okay, today we're going to talk about the mole. Now I know what you're thinking. I know what a mole is. It's a small, furry creature that digs holes in the ground and destroys gardens. And some of you might be thinking that it's a growth on your aunt's face with hair sticking out of it. Well, in this case, a mole is a concept that we use in chemistry to count molecules, atoms, and just about anything extremely small. Have you ever wondered how many atoms there are in the universe, or in your body, or even in a grain of sand? Scientists have wanted to answer that question, but how do you count something as small as an atom? Well, in 1811, someone had an idea that if you have equal volumes of gases at the same temperature and pressure, they would contain an equal number of particles. His name was Lorenzo Romano Amadeo Carlo Avogadro. Wonder how long it took him to sign autographs. Unfortunately for Avogadro, most scientists didn't accept the idea of the atom, and there was no way to prove he was right. There was no clear difference between atoms and molecules. Most scientists looked at Avogadro's work as purely hypothetical and didn't give it much thought. But it turned out he was right. By late 1860, Avogadro was proven correct, and his work helped lay the foundation for the atomic theory. Unfortunately, Avogadro died in 1856. Now the thing is that the amount of particles in even small samples is tremendous. For example, if you have a balloon of any gas at 0 degrees Celsius and at a pressure of 1 atmosphere, then you have precisely 602 sectillion gas particles. That is, you have 6 with 23 zeros after it particles of gas in a container. Or in scientific notation, 6.02 times 10 to the 23rd particles. This example is a little misleading because gases take up a lot of space due to the high kinetic energy of the gas particles, and it leaves you thinking atoms are bigger than they really are. Instead, think of water molecules. If you pour 18.01 grams of water into a glass, which is 18.01 milliliters, which is like 3.5 teaspoons of water, you'll have 602 sectillion molecules of water. Since Lorenzo Romano, never mind, Avogadro was the first one to come up with this idea, scientists named the number 6.02 times 10 to the 23rd after him. It is simply known as Avogadro's number. Now, back to the mole. Not that mole. This mole. Yep, this number has a second name, the mole. Chemists use the term mole to refer to the quantities that are at the magnitude of 602 sectillion. This is known as a molar quantity. Atoms and molecules are so small that chemists have bundled them into groups called moles. Moles are hard for students to understand because they have a hard time picturing the size of a mole, or a 602 sectillion. It's just too big to wrap our brains around. Remember our 18.01 milliliters of water? Well, that's a mole of water. But how much is that? Exactly what does 602 sectillion look like? Maybe this will help. Exchange the water particles for donuts. If you had a mole of donuts, they would cover the entire Earth to a depth of 8 kilometers, which is about 5 miles. You'd really need a lot of coffee for that. If you had a mole of basketballs, you could create a new planet the size of the Earth. If you received a mole of pennies on the day you were born and spent $1 million a second until the day you died at the age of 100, you would still have more than 99.99% of your money in the bank. Okay, now we sort of have an idea how large the mole is. So how do we use it? You might be surprised to know that chemists use it the same way you use pounds to buy grapes, deli meat, or eggs. When you go to the grocery store, you don't go to the deli counter and ask for 43 slices of salami. You buy your salami by the pound. When you buy your eggs, you buy a dozen eggs. When we hear the word dozen, we probably think of the number 12. We also know that a pear is 2, a baker's dozen is 13, a gross is 144, and a ream of paper is, anybody? A ream is 500. Well, a mole is really the same thing. For a chemist, a mole conjures up the number 6.02 times 10 to the 23rd, not a fuzzy little animal. The only difference is that the other quantities are more familiar to us. So there you have it, the story of the mole, Avogadro, basketballs, and how to buy salami at the grocery store.
Okay. There it is. All right. Okay, so that's what the mole is then. It's a number, it's an amount of something. Okay? And it becomes a conversion factor. 1 mole equals this many atoms or molecules or particles of something. Okay? And we can be able we can start to, if I'm given 2.56 times 10 to the 10 to the, let's say, 12th atoms of carbon, then I can figure out how many grams that should weigh. Because this is a conversion factor. It's a conversion factor, and the conversion factor for carbon is right here. 12.011 grams of carbon for every how many atoms? This 12.011 grams of carbon is for how many atoms of carbon? Not a single atom. That's atomic mass, but grams, if it was 12.011 atomic mass units, that would be different. That would be for every single carbon, but it's not. This is in grams. If I weigh 12.011 grams of carbon on a scale, do I have 1 atom of carbon? No, absolutely not, right? If I weigh 12.011 grams of carbon, how many atoms of carbon do I have? I have 1 mole of it, which is how many? I know you guys want to say it. I can hear the the snake sounds coming out of your mouth. Okay, 6.022 times 10 to the 23rd atoms of carbon would have a mass of 12.011 grams of it. So if I measure out 40.08 grams of calcium, 40.08 grams of calcium would have how many atoms of calcium? .022 times 10 to the 23rd atoms of calcium would have a mass of 40.08 grams. What if it was 20.04 grams of calcium? How many atoms would I have? Exactly half of that number, right? I'd have half of those. Okay. So it's a conversion factor. So if I have 2.56 times 10 to the 12th atoms of carbon, how many grams is that? Well, I have the conversion factor right on the periodic table. Atoms to grams from the atoms. Cancel out my atoms, and I'm left with grams. There are 12.011 grams of carbon for how many atoms? There we go. That times 12.011 divided by 6.022 times 10 to the 23rd, that's going to tell me exactly the mass of 2.56 times 10 to the 12th atoms of carbon. Okay? So these numbers are conversion factors. They allow you to convert from one thing to another thing. All right? It could be moles too, because that 12.011 grams is per every 1 mole. So it could be 36.5 grams of carbon, and I want to convert that to the moles of carbon from the grams of carbon. Well, there's 12.011 grams of carbon for every how many moles? That's the atoms. How many moles? 1 mole. That's what these numbers represent. Grams for every 1 mole. And how many atoms are in a mole? 6.022 times 10 to the 23rd atoms in every mole. That's why there's 12.011 grams in every 6.022 times 10 to the 23rd atoms. Or there's 12.011 grams in 1 mole. So whenever I see mole, that's the number I'm going to use. Whenever I see atoms, that's the number I'm going to use.